Hi, this is Mrs. Berlinghoff, and this is Geometry, Chapter 11, Section 4, Areas of Regular Polygons. You have to forgive me for using the video camera here. My pen that I usually teach these lessons with is not working right now. I'm waiting for a replacement. So I'm just going to do the best I can with the videos. So for those of you who have been absent and might have missed this lesson, you have a chance to watch me teach it again here with the video. It's not quite as good as being in class for it, but it's better than nothing. Let's see how it goes. Okay, so if we're going to find areas of regular polygons, we better be able to define regular polygons. Okay, regular polygons are equiangular and equilateral. That means that they have all equal angles and all their sides are the same length. Okay. And we've studied those before, so that's just kind of a review. Our second objective here is to discover and use formulas for finding areas of regular polygons. And we're going to start with the equilateral triangle. Keep in mind that an equilateral triangle could be called a regular triangle because all three sides are the same length and all three angles are 60 degrees. So as we look at this figure right here, if this is an equilateral triangle, all three angles are 60 degrees. So if we use our formula for the area of a triangle, which is base times height divided by 2, or 1/2 times the base times the height, what we're going to do is draw in a height right here, and we create those two 30, 60, 90 triangles inside. So whatever this side is here, we're always going to be dividing it by 2 to get the short leg, and then taking half that side and multiplying it by radical 3 to get the height. So the height will always be the side divided by 2 times radical 3, and the base, where this box sits, is always going to be equal to the side length because all three sides are the same. So that means replacing that in our triangle formula, we can make a formula specifically for equilateral triangles. 1/2 times the base, which is always the side, times the height, which is always the side divided by 2 times radical 3. And that simplifies to the side divided by 2 squared times radical 3. So let's do an example. If you have an equilateral triangle with a side length of 12 inches, you can plug it easily into this formula. Divide your side length by 2, square that, and multiply it by radical 3. 12 divided by 2 is 6. 6 squared is 36. 36 times radical 3 is 36 radical 3. And of course your units are squared. Now, we started off with regular triangles, or equilateral triangles, because our third objective is to find the areas of regular hexagons. Now, here's what's interesting. A regular hexagon can be inscribed in a circle, which we've done right here. And what you do to create a regular polygon, specifically a hexagon inside the circle, is to draw the circle, mark off your center, and then since a hexagon has 6 vertices, you would mark 6 points on the circle that are all 60 degrees apart, because 360 divided by 6 means that they're 60 degrees apart, which means that each central angle that contains those 60-degree arcs is also 60 degrees. Since these are radii here and here, it means that these angles are congruent here and here, and therefore, when we draw those radii, we created 6 equilateral triangles, which is very convenient because we have an area formula for equilateral triangles. Since a hexagon has 6 equilateral triangles in it, we can find the area of a regular hexagon by taking our equilateral triangle formula and multiplying it by 6. Isn't that convenient? It's not the only way to find the area of a regular hexagon, but it's certainly a sensible way to do it. If you know what the side length is, you can easily tell what the area is by using this formula. So let's do an example. Let's find the area of a regular hexagon with a radius equal to 8 inches. So notice up here, let's just look back here. Here's like what you would call the side of the hexagon, okay? But remember, we said that these were all equilateral triangles in here. So the side of the hexagon has to be congruent to the radius, or else these 6 triangles are not equilateral, correct? So, in place of the radius, we could use side or vice versa. So, for this problem here, we're going to plug in our 8-inch radius in place of the side, because the side is congruent to the radius. 8 divided by 2 is 4. 4 squared is 16. 16 times 6 is 96 times radical 3 is 96 radical 3 inches squared. And that's the first 2 objectives, or first 3 objectives rather, of section 4, chapter 11.